Mechanics Lesson 4, Conservation Laws. We've talked before about the conservation of energy, or really the conservation of mass energy equivalents. We've talked about why it has to be that way. Because if it wasn't, yesterday wouldn't be the same as today. Today would not be the same as tomorrow. If I could take 100 joules of chemical energy, turn it into 120 of kinetic, and then back into 120 of chemical, and then to 160 of kinetic, and so on and so forth, we'd very quickly have infinite energy, and everything would sort of explode. The inverse is also true. If I went to 100 to 80 to 60 to 40, then all the energy would drain out of the universe, and everything would sort of stop. Conservation laws allow us to make predictions about the future. They allow physics to be the same day in, day out. And it turns out that the universe has quite a lot of other things it's keeping track of, not just mass energy. There's lots of other things which turn out to always be the same amount of this thing across the whole universe. We're going to have to learn a lot of different conservation laws in order to get through quantum mechanics. Quantum mechanics is where most of these conservation laws happen. The only one that's really Newtonian would be momentum, which is always, always conserved. So today we're going to be looking at three: mass, energy, charge, and this strange one here, lepton number. So when we're talking about mass energy, we've already seen that, but it's going to come up a lot more in quantum mechanics. Whenever a large particle is decaying into a smaller particle, we've got a gap there. We've lost some mass. So therefore, we're going to need to have some energy coming out to make up the difference. On the inverse, occasionally, if we want a smaller particle to turn into a bigger one, we need to put some energy in to make that mass up. This difference between masses, whenever we lose mass that's turning into energy, is called the mass defect. The mass defect. Now, we're not going to do any questions on that until next year. Just want to put a seed in your mind to remember that. So, charge. Charge is also conserved throughout the universe. We've seen this in the previous video. When a neutron turns into a proton, well, we've got no charge before, so we're going to want no charge afterwards. So we're going to have to add an electron. And then we've got no charge before, no charge afterwards. When a proton turns into a neutron, well, we're going to need a positive electron again to balance out the charge. So charge, always, always conserved. Now we have this strange thing, lepton number. This is more of a concept than a real thing. It just turns out that the universe also conserves this. A good way of thinking about it is the total number of electron-y things is always constant. Okay? So, what does this mean? Well, lepton number is conserved across all leptons. So there's a thing called the electron lepton number, which is always conserved, and later on we'll learn other ones like the muon lepton number, which is conserved independently of the electron lepton number. So electron lepton number is a quantity like charge or mass which is conserved in of itself. Electrons have an electron lepton number of 1. So an electron has an electron lepton number of 1. A positron has an electron lepton number of -1, which is what you'd expect. So before, in this one, we've got no electron lepton number, but now we've added an electron, which is got an electron lepton number of 1, so now we've got an imbalance in our equation. So we need to add in something else. And what we add in is an electron neutrino, which have an electron lepton number of 1, but we make it anti, which is what this line means, and then this has an electron lepton number of -1, so overall these make 0. On the flip side, if we've got a positron, which is an electron lepton number of -1, we need to add just just a normal electron neutrino, because this has a lepton number of 1, an anti-1 -1, and therefore you can see if we have this pair or this pair, we'll be back to the 0 on this property which we are tracking. This, of course, asks the questions, what are neutrinos? Neutrinos are incredibly fast-moving, very, very light particles which basically carry whatever energy and lepton numbers we need them to make the maths work. They're the sort of remainder at the end of the equation, these strange little particles which we just find, keeping everything in check, making sure everything works. They're incredibly penetrative neutrinos. They fly straight through the world and out the other side without interacting with anything. So they go very, very fast and don't really interact with much. In fact, the main thing they're going to do is interact with each other, as we'll find out in the next video. So just to recap, mass energy is conserved, that's easy. Charge is conserved, a little bit more difficult, but the neutron's turning into proton, we need negative charge. Proton's turning into neutron, we need a positive charge, simple as that. And then electron-lepton number is also conserved. So if we're making an electron, we're going to need an anti-electron neutrino to balance it out. If we're making a positron, we're going to need a normal electron neutrino to balance it out. See you in the next video.